Okay, the last type of hydration reaction that I'd like to talk about in this video is called hydroboration oxidation. The first step here is hydroboration, which is exactly like it sounds. You're adding hydrogen to one carbon and boron to the other carbon, and then we oxidize the carbon-boron bond to a carbon-oxygen bond. But notice that the difference here is that we start with an alkene, we hydrate the alkene, but now the hydrogen goes to the more substituted carbon, and the OH goes to the less substituted carbon. So this you could think of as the anti-mark product. This is the opposite of what you would see with acid catalyzed hydration. This is the opposite of what you would see with oxymercuration, demercuration. But if we understand the mechanism, then we can understand exactly why we get this unusual result. Before we talk about the mechanism, though, I want to talk about the stereochemistry, because this is a little bit different than what we've seen before. Again, because we actually don't have a carbocation intermediate in this reaction, we can get some selectivity here. So notice we still get a racemic mixture, but what's important to note here is that the hydrogen that was added to the alkene and the OH that was added to the alkene are on the same side. Even though we get a mixture of enantiomers, they both have a cis relationship of the hydrogen and the OH. This is called the syn product, and this one is also called the syn product, meaning that the hydrogen and the OH are together. You could think about this as the cis product. This is called a syn addition, meaning that they're together. Both the OH and the H are on the same side. Once we understand the mechanism, this will make perfect sense. Okay, so the first step in the mechanism is called hydroboration, and this is the very easy step to understand. If you think about borane, BH3, boron has 6 valence electrons, right? And we know by the octet rule that an atom wants to have 8 electrons. So boron has an empty p orbital, which we can sort of draw like this, which is coming in and out of the page, which can accept electrons. Boron is a good electrophile. It's actually a Lewis acid. It wants to accept a pair of electrons. It has this empty orbital that can accept 2 electrons. Okay, so let's say an alkene comes along. It has 2 electrons that it wants to donate to that p orbital that boron possesses. So what happens? These 2 electrons flow into that p orbital, right? But when we do that, we start generating a positive charge here. And so these 2 electrons are attracted to that positive charge. So notice what's happening here is that in Mark's rule, right, the electrophile always goes to the less substituted carbon to generate the more substituted carbocation. That's exactly the same thing that's happening here. The only difference is that in this reaction, boron is the electrophilic atom, and hydrogen, in this rare case, is the nucleophilic atom. So the nucleophilic atom always goes to the more substituted carbon, and the electrophilic atom always goes to the less substituted carbon. So what do we get here? We get hydrogen on the more substituted carbon, and we get boron on the less substituted carbon. And this can happen for all the boron-hydrogen bonds. So this can keep continuing to happen with other alkenes. So in the presence of other the other starting materials, we get a trialkyl borane, which would just look like boron with 3 alkyl groups like this, right? So this is where we're at the end of the hydroboration step. Now what we need to do is replace this carbon-boron bond with a carbon-oxygen bond to give the alcohol. Once we do that, once we oxidize this, then we'll have the alcohol that we observe in the product. Okay, so how does that work? Well, let's look at this for a second. On the last slide, here's where we left off. We have this, and we have this, and we have this. And what's going to happen is we're going to add sodium hydroxide and hydrogen peroxide, HOOH. And what we're going to get here is replacing the carbon-boron bond with a carbon-oxygen bond. So notice that what we've done is we've gone from an alkene, we hydroborated it to get this product, then we oxidized it to get this product, so we added a hydrogen to the more substituted carbon, we added an OH to the less substituted carbon. So let's look at the mechanism of this step. When we take sodium hydroxide and hydrogen peroxide, what can happen is an acid-base reaction where hydroxide deprotonates hydrogen peroxide to make the O minus right here. And so if we have a OOH minus, now this can attack boron. Remember, boron still has an empty p orbital that can accept electrons. And when we do that, we get boron OOH. Turns out that the oxygen-oxygen bond is one of the weakest bonds that we're going to study in organic chemistry. So this bond really wants to break. So what can happen is this carbon-boron bond can migrate over to the oxygen, and when it does so, we break this bond. So the result here is that we have a boron-oxygen bond, that's still there, but now this carbon is bonded to this oxygen because it moved over. We still have these two guys on there. And we can continue to do this over and over again until we've substituted all the carbon-boron bonds for carbon-oxygen bonds. So this can happen over and over again. And so that I have room, I'm going to erase what I've just drawn and start from scratch here. So let's imagine that we take this and we keep on reacting it with more hydrogen peroxide, and we keep getting this migration to happen over and over again. What's that going to look like? Well, eventually we'll hit boron with 3 OR groups on it. We had sodium hydroxide present, so the hydroxide can attack the boron. Now that we've exhausted all the OR groups, now we can get a species that looks like this. And an OH. Boron is negatively charged. In order to get rid of that negative charge, one of these groups can leave. And so we have an O minus. And then there's water present in the reaction. So protonation of this finally gives us the alcohol product that we observe. So notice we've added a hydrogen to this carbon and an OH to this carbon. That's hydroboration oxidation. Okay, remember that this is a syn addition, but just because it's a syn addition doesn't necessarily mean that we're going to get any excess of one enantiomer of the other. This alkene is flat, so hydroboration can happen from one face of the alkene or the other face, and depending on which face of the alkene that the boron adds to, we can get the boron adding from the top or the boron adding from the back. So we're still going to get a mixture, a racemic mixture of alcohols from this particular reaction. Okay, so to summarize here, we talked about 3 types of reactions to hydrate alkenes, and depending on what result that you want to choose the appropriate hydration reaction. So In one case, what we can do is what we call acid catalyzed hydration. In this reaction, elements of water are added across a double bond. It's the reverse of the E1 reaction, so we can influence the reaction depending on how much water is present. Like I said, the equilibrium can be controlled by Le Chatelier's principle. But the downside to this reaction is that the carbocation that's generated is prone to the types of rearrangements that we're already familiar with. In order to avoid those rearrangements, we can choose to do an oxymercuration demercuration. The advantage to this reaction is that it doesn't go through a carbocation intermediate. It proceeds through a three-membered ring mercurium ion, or mercurium ion. And since there's no carbocation involved, you don't see rearrangement. And then the demercuration just occurs with sodium borohydride. The last type of reaction that we talked about was hydroboration, oxidation, and this gives the anti-mark product, where the OH goes to the less substituted carbon. So we have OH on the less substituted and the hydrogen on the more substituted carbon. So this is nice because it's the opposite of both acid catalyzed hydration and oxymercuration demercuration.